This is a lesson on thermal expansion in the heat and thermodynamics unit. Up until this point, we have seen how heat transfer causes different physical results. Heat transferred to an object may cause a change in the physical dimensions, and this is not a phase change. This is just a change in just the dimensions of the object. This is how a thermometer works. Over here is an example of maybe a thermostat or a turn signal where I use two different substances. When heated, expand at different rates. And so you will get this curving to one side because the one substance here will expand more than the other substance, and so it curves. And down here you can see if there's a cool temperature and a hot temperature, there's some sort of increase in length. You see this effect on sidewalks. The cooling and then heating in the summer, cooling in the winter will cause that concrete to expand and to contract, and that will cause damage within the substance, etc. But that's why there's little space left in order to accommodate expansion in the summer and then contraction in the winter. Quantifying thermal expansion is given by a couple of equations. There is just the plain length equation. When you think about the length changing, this is linear. We can see that there's, which I have in the picture here, the original length. It could be a cold substance. If the original length is large and you have a decrease in temperature, you're going to get a smaller amount, a smaller length. So delta L is the change in length of the object. L naught is the original length. And here, delta T is the change in temperature. There's the last thing here. Remember, this is Greek small case alpha. Greek small case alpha is the coefficient of linear expansion, and this depends on the substance. Some substances can take in more heat and take a temperature change and not change much in dimension, and then others may change a lot. And so that is how that is quantified in the equation, and this depends on the substance. There is also a volumetric expansion equation. You can see that instead of L, there's V in here for volume. And instead of alpha, there's a beta, where beta is the coefficient of volume expansion rather than linear expansion. Beta is Greek letter beta here. It's a small lowercase letter. And beta is often given in problems. You can approximate it to be 3 alpha, but it's often given in problems. So that's how you quantify that relationship. I've picked a problem to exemplify this, and there's the equation here. Suppose a meter stick made of steel and one made of Invar, an alloy of iron and nickel, are the same length at 0 degrees Celsius. So I'm going to note that, 0 degrees Celsius. What is their difference in length at 22 degrees Celsius? And they give us the alpha, the coefficients of linear expansion for these two substances. I've put here delta L equals alpha L naught delta T. I'm going to note that each one is a meter stick, so L naught for the steel equals L naught for the Invar, which is 1 meter. I'm also going to note that T initial for both of these is the same. T Invar for initial for the steel equals T initial for the Invar, which is 0 degrees. T final for the steel equals T final for the Invar, which is 22 degrees. So when I think about a delta T for the steel, it will equal delta T for the Invar, which is 22 degrees Celsius. That's the temperature change for them. Okay, so when I look at putting this equation together, or when you're looking at it, it may be your knee-jerk reaction is to find the change in length for the steel and then the change in length for the Invar, and then you could subtract those two things. You'd find this as a number and then find this as a number. And I don't think you're wrong doing this, right? You can do alpha for steel, L naught, which we know is 1, delta T for the steel, and then set the other one will be for Invar, delta T Invar. So they have similar terms in there. These L naughts are the same, and the delta T's are actually the same as well, right? We said those are the same. But what we really want is, what is their difference in length? We don't really care about how much they expand. We care about the difference of their expanded lengths. So I'm going to call it delta delta L. The delta of delta L will equal delta L for the invar minus the delta L for steel. And I put invar first because I see that invar has a larger coefficient of linear expansion. It's going to expand more. So I put it first, and when I subtract these two things, I'm going to get a positive number. I'm going to put what I know for each of these in. Delta L invar is going to be alpha invar, L delta T for the both of them. That's the same thing. I'm going to subtract off alpha for the steel, L delta T, and we can see that L delta T is the same in both of these equations. So I'm going to factor that out and leave the alphas in there. Alpha invar minus alpha steel, original length delta T. So this becomes a much easier calculation than if you're doing each one separately, I believe. Okay, so I'm going to take 14.6 minus 11 times 10 to the negative 6. I just did that real quick. They're both to 10 to the negative 6, so I'm going to take 14.6 minus 11 and then still have 10 to the negative 6th here. L naught is 1. Delta T is 22. And you're getting the feeling here. We have 3.6 times 10 to the negative 6 times 22. So the difference in their lengths, the changes in their lengths, is going to be 79.2 meters. If you wanted to double check, the expansion of the steel is 242 micrometers. So in the end, it'll be 1.000000242 meters. That's how long it would be. And you could calculate this number. And you can see why I went ahead and just did it this way rather than calculating the two numbers separately. The expansion here is 321.2 micrometers. This is 10 to the negative 6. So the new length of the invar meter stick is going to be this. And when I subtract these two, I get this value. That's their difference in length. So instead of actually calculating their new lengths, I found the difference in their expansions, and that will be the difference in their lengths as well. It's just a little bit quicker way to calculate that. And that's how you would use that equation. Pretty straightforward.